I'm Dan Olds, and today the subject is weather forecasting in WRF. This is one of the applications that's going to be used in the upcoming student cluster competition at ISC, and it's an application that's been used in student cluster competitions in the past. And today we are very, very fortunate to have Dr. Jordan Powers and Dave Gill with us to talk us through what WRF is and how to make the thing sing. Jordan, say hi and tell us a little bit about yourself.
Hi, Dan. I'm Jordan Powers, and I'm a scientist here at the National Center for Atmospheric Research in Boulder, Colorado. I do computer weather forecasting, which technically is known as numerical weather prediction. And the model that you mentioned, which is called WRF, is a key tool in doing this today.
Excellent. Dave, say hi.
Howdy do, everybody. My name is Dave Gill. I'm one of the software engineers that support the WRF modeling system. What I do here is primarily as a software engineer, I work on the source code structure, the Fortran, the C, the language interface, the scripting to get the whole build mechanism. And I'm also part of the user services team because there are about 20,000 folks out there that have downloaded and used the WRF for their daily forecasts.
You two are definitely the right folks to talk to, I would say. You seem to know your way around this a bit.
Well, both Dave and I have been doing it a long time. I'm more of a scientist and use the model for forecasting and analyzing the weather and studying meteorology. And Dave is one of the guys who has built this system, and he knows very well the software and hardware background and needs for it.
Excellent. To start, what is WRF? How does it work?
WRF is how we pronounced the acronym WRF, and these letters stand for Weather Research and Forecasting. And the model is called the Weather Research and Forecasting Model, and it's a set of computer code that really simulates the atmosphere and its evolution, which is the weather in layman's terms. So this model has existed. It was first released in 2000, and it's evolved since then. And it is probably the most widely used model of its type to forecast the weather in the world. It is used by official government agencies for official government forecasting. For example, the National Weather Service of the United States. It's used by foreign governments as well. The other segment of users is that of folks in research, and they use it to simulate the atmosphere to study things like hurricanes and tornadoes and winter storms, and whatever you can think of, they will try to recreate with this model. It provides three-dimensional data sets with weather information that points throughout the atmosphere, and with this detailed information, we can really get a good picture of how things behave.
Or how things would behave under certain conditions.
Correct. It can be used to set up idealized scenarios or go back and recreate certain events to understand what happened.
And this is under the category of one hell of a complex model.
It is. Dave, perhaps you can tell us how big WRF is, but it is. It's very computer intensive, and we run it on the fastest supercomputers. But Dave, can you tell us about what WRF looks like underneath the hood?
Sure. It's about 500,000 lines of code if we just talk about the model proper itself. It's primarily written in Fortran, and there's some C code that's inside to help us build the code itself. The building mechanism, when the folks start getting involved in this, is located inside the WRF directory. There's an ARCH and ARCH directory. Inside there's a configure_new default. That's where people are going to start putting in their modifications if they want to play around with and do some tuning for the way that the model is going to behave. Once you do the configure command, you end up with this configure.WRF file. That file has all of the compilation options that the folks are going to need to modify. Right now, if you look at WRF, we have some people who are making efforts to try to add some GPU and some mic technology, and it's not available for prime time yet. One of the problems with WRF is that it's fairly flat, so that there really isn't anything that sticks up that you would want to say, okay, this I'm going to throw over to a GPU and get it to process this. The dynamics is about 30 or 40%. The physics is about 40%. The infrastructure and the I/O usually take up the balance of that. So there's no nail that sticks way up in the air that you want to identify. One of the pieces when you're messing around with the WRF code is there are enough things that are unknown about the atmosphere that you really don't have to say, I'm going to run these things in double precision. So using 32-bit floating points for folks is going to be just fine. The WRF model decomposes quite well. There are people who have run the model on a suitably large enough domain size, up to several tens of thousands of processors, and heading towards 10 to the fifth processors and such. What WRF will do is it will, as any application, it'll tend to knee over in performance if you get to a point where there's not enough work for the to amortize the amount of communications that you're doing.
So it does scale out pretty well. It's fairly parallelized.
If you have a big enough job, WRF will scale quite well. So depending on what the people who are constructing the problem for the students throw at them, depends on how many processors they could make effective use of. There's a few rules of thumb that you can take advantage of. The WRF model, you can consider it to look like the domain to look like a checkerboard, and the red and black squares are individual cores that are running or solving equations, and in between those squares or those rectangles, communication has to take place, but interior, the model is able to be fairly independent. The more of those checkerboards that you're able to decompose the model into, faster the solution, unless the amount of communication is going to dominate the amount of time it takes to do the computation inside.
So that's the trade-off. Students are going to have probably between 6 and 12 nodes and anywhere up to a couple of hundred cores, and some of their configurations are going to have GPUs because that's going to be useful on other workloads. Do you think that this is primarily a matter of how they set the problem up on the system, how they decompose it?
I think you're definitely going to get an impact on the decomposition. For example, if you have a total of, let's say, do a simple number, 32 total cores, the WRF by default will decompose the domain. It'll take the two factors closest to each other. For 32, it'll be 8 and 4, and it's going to decompose the y dimension by the largest of those 8 and the x dimension by the smallest of those 4. We do that because the first dimension that we run on WRF is the fastest incrementing, and we want the longest run inside of cache. So if you have 32 processors, it would be an 8 by 4 decomposition. If you just say, okay, well, I'll do 3% less, I'll do 31 processors, then it's a prime decomposition. What you end up with is the entire X running in a single run and decomposing the Y direction by 31. So by just changing 3% of the number of processors, and you certainly wouldn't get a 3% hit in performance, you change drastically the decomposition strategy. And if it turns out that having a much longer run in your cache provides you some advantages, you can see some real benefits just choosing to add or subtract a couple of extra cores in your job.
What we don't know, and as we discussed in our pre-call, we don't know exactly what the organizers are going to throw at them. We believe that they'll throw them a data set and a result they need to get to, and that the students will probably have enough time to do several iterations in order to arrive at the fastest runtime they can get to. Putting yourself in the student's place, or as probably more likely a very highly paid consultant to the students, what would you guys recommend that they do first when they first get that data set and their requirements?
I guess I'll speak first, Dave, and I'll talk about physics a little bit, and then Dave, you might weigh in on hardware and software configuration tips. The weather model has a lot of options for how to represent processes in the atmosphere, and these can return differing levels of accuracy and goodness of the forecast. But it can be simplified quite a bit by selecting options to minimize the amount of computation and the amount of detail that's putting into the forecast. So as a general rule of thumb, I would look toward the simpler physics options that may be mentioned in the WRF literature. But as Dave mentioned, one might assume that the organizers of this are just going to say run this particular configuration, because it gets into a different exercise to have the students try to guess which physical processes are going to be more time-consuming on the computer than others. So I think that probably pushes it more into the realm of how to structure this thing and how to set compiler options, which I guess, Dave, you could probably speak to a bit better.
One of the things that I would do if I was first given the task is I'm assuming that most of the participants have already started building and running the WRF code.
Yes.
So maybe in advance of them receiving the instructions on the day of the competition, I would say ahead of time, I would make sure that I had things that were as optimized as possible. The WRF code is able to be built or is able to run in parallel, and it can have two different modes of decomposition, distributed memory with MPI and also shared or threaded with OpenMP. I would say it would be a good idea for students to take some test data sets and run on both of those configurations on their machine and see which one they're getting the best results for.
Mm-hmm.
They can look on the WRF user page. If they just Google WRF User Guide 3.5, they'll get a user guide that has all of the information about the WRF system. Particularly in Chapter 5 is the information on the WRF model itself.
Yeah.
The way that they can determine whether or not the model is behaving as well as possible, or if a change is providing any sort of improvement, is the model will dump out these output files, and they're called RSL for Runtime System Library .out, and then with 4 numerals after it, and the master node is 0000. Looking in there, it tells you the amount of elapsed time it took to do each time step. So if you do a dozen time steps and change some compiling options, run those same time steps again, you'll be able to see the amount of elapsed time that it took to do those processors by changing from 32 to 33 to 31 cores, from doing 32 cores with some of them with OpenMP, some of them distributed memory. Those sorts of pre-tests are things that I think are going to provide a real benefit for users. The WRF model by default will output all of the data from the master node. So when they are designing their system, even if they probably don't need to have a I/O hooked up to each one of the cores, but if they have a fast interconnect, it's probably going to be required because all of the data has to drain to the master, and the master's going to be the guy that does the output. As far as seeing if things are working out the day of the experiment, I would go ahead and go with their previous tests that they've conducted, that they know this tends to be a sweet spot for the production run. And the model will have a bend in the performance when it starts the amount of communication starts to get high. But it will probably go a long way before it bends over backwards, and actually adding more processors increases the amount of time. So you may not get to an efficiency level that you want, but time to solution will usually decrease by adding more and more and more processors to it.
That's really good advice in there, and I'll throw up a link in the video version to this. I'll also throw up some examples of weather so they know what that looks like. This is great stuff, guys. Any final tips or traps or anything that they should be aware of?
Well, Dave mentioned an excellent strategic thing is just to run WRF in advance.
Yeah.
If they have the data in advance rather than trying to learn things in a 12-hour block.
They won't have the data, but they will have, there's example data sets up there.
Oh, okay.
Or there are example data sets out on the web, I'm sure.
Yeah, from the WRF page, which is www.mmm.ucar.edu/WRF/users. There are many links there, and there are canned cases that potential WRF users can pull down to run. Dave may agree with this. If they have a range of compilers that they are thinking on running on the hardware and systems that they've created, they could in advance take a sample WRF data set and try the different compilers to see which one yields the fastest executable. That's an idea that comes to my mind.
Good
they
one.
may find that Intel is running faster than PGI or running faster than GNU. Dave, could you speak to that maybe?
Right. Like Jordan said, if the participants before the day of the competition, when they are looking to try to help themselves as much as possible with WRF, there is a good amount of information on the web. And the website that Jordan listed has cases that you can download. If you look for WRF benchmark, there are a couple of at least test data sets that are a little bit larger that users can download and run through the system to make sure that things are working as well as possible. When the users do modify the runtime configuration, you can make a substantial difference with optimization levels, and as long as the model is able to stay stable, I think they should be okay. We've seen some compiler options that don't give us bit-for-bit reproducible results, but for this competition, that would probably be acceptable. The MPI and NetCDF libraries that the team is going to download, they probably are going to be able to choose their distributed memory library, OpenMPI or MPitch, for example, and they can probably choose which version of NetCDF they're going to play around with. With NetCDF, if they choose to do data compression, that could probably save them a significant amount of time for I/O. And that data compression is a standard option, and it's available inside of WRF, and it cuts the data down by maybe a factor of 2. And if I/O is an issue, that's something they can certainly take a look at. But if they're going to get in there with the nitty-gritty and start messing around with the compiler flags, that'll be in that configured out WRF file. Other than those two guys, the decomposition would be a real place to spend some time.
So that's something that they thoroughly want to understand. Hey guys, this has been great. Now, are either one of you going to be at ISC?
I will not.
No. How about no? I will not.
That's too bad, because it'd be great to have you guys there as color commentators. I'd get you blazers.
That'd be nice.
Just be like Wide World of Sports. We could walk up and down and talk about what's happening in the WRF world right now as they're running it.
What's the venue? And where will it be?
Oh, it's in Leipzig, Germany, in the middle of June.
Wow, that'd be super.
As soon as I sell this whole concept of covering student cluster competitions to ESPN, probably like ESPN 8, then I'll see if I can get some budget to get some commentators over like you guys.
That'd be super. If there were a budget for this and our schedules permitted, we'd love to do it.
And again, I'd get blazers. We'd have matching blazers, which I think would be great. Well, this has been great, guys. Thank you so much for the time. And there's some real serious nuggets of wisdom that you've passed along to the students and stuff that they should be paying attention to in the 2-week run-up to the competition. Thank you guys so much.
Thank you, Dan. It's been great talking to you.
Just want to wish the contestants the best of luck, and may Navier-Stokes and finite differencing force be with them.
Perfect words to close on. Thanks a lot, guys.
Thank you very much.